Okay, now we're going to talk about Faraday's law, which is the mathematical formulation of Lenz's law. Faraday's law says that the electromotive force, or the EMF, produced in a closed loop is equal to the negative of the time rate of change of the external magnetic flux through that loop. So this term right here is the same flux that we've been using. This dF indicates a change. That's what we've been talking about. And the negative indicates that the EMF is opposite or has a different sign relative to the change in the flux. Now the EMF is a funny word, but it means electromotive force, and it's essentially just like a voltage. It is a force applied to the charges in a current loop and moves them around the loop, and can be used in circuit calculations in the same way that a voltage can. And we'll be learning more about that later. Now the next part of Faraday's law has to do with the sense of the EMF, and that implies the direction in which the current would flow. The current that is created, the induced current, which direction does it flow? And that's determined by the sign of the EMF and using a right-hand rule. So basically, in the case where the A vector is pointing up, as in both of these cases, for a positive EMF, the current flows this way, which is given by the right-hand rule. For a negative EMF, it would flow in the opposite direction. The best way really to see, to understand how to use this law is through examples. So let's consider this example. And what I'm going to do is I'm going to draw some images of the circular loop in its initial and final state. And I'm going to imagine I'm looking down on the circular loop. And remember, the circular loop is above a north pole of a magnet initially. So the north pole has the magnetic field pointing out of it. Since we're above it, that means that the magnetic field will be coming out of the page initially. This is in the initial situation. Now in the final situation, the magnet has been flipped over, and now the magnetic field is pointing towards the magnet, so it goes into the page. So let's list some of these quantities we have here. We know that the magnetic field magnitude is 13 microtesla. The radius of the circular loop is 4 millimeters. And the time it takes to flip over is 0.43 seconds. Now I need to define a area vector here for this. So what I'm going to do is I'm going to define an area vector for the loop. Let's put it right here, and I'm going to point it in the direction of the magnetic field, so it's pointing out of the page here. Now we're going to apply the law here. The law says that the EMF will be minus d phi dt. Now in this case, since we're giving a finite time period and we're asked about the average will be the delta phi, the finite change in the magnetic flux divided by the delta t. So now we just have to figure out the initial and final fluxes. So this will be minus final flux minus initial flux over delta t. Alright. Since the magnetic field and the area vector are pointing in the same direction initially, we know that initial flux is going to be positive. So let me put my minus sign here, and let me expand now these terms in terms of the area and the magnetic field vector. So the initial or the final flux here is actually going to be negative here, right? Because the B field is into the plane, but the A vector is still out of the plane. The A vector is still the same. In fact, if you want, I can write it again here. just to emphasize that point, because the loop hasn't changed. The loop has not rotated or changed at all. So the final flux would be A times B minus the initial flux. The initial flux here, again, is positive because A and B are in the same direction, and it has the same magnitude, A times B, divided by delta T. Let's move this up a little bit. So now that we have our equations, we have the EMF as just 2AB over delta T. That's 2. The area of the circular loop is pi r squared times B over delta T. This equals 2 times 3.14 times 0.004 meters squared times 13 times 10 to the minus 6 Tesla. That's divided by 0.43 seconds. And this equals, you can verify for yourself, 3.0 nanovolts. Notice that the units are the same as the units of potential. Okay, the second part of the problem is to determine the direction of the current. If you look back here, it says, what is the direction of the induced current? So let's see if we can figure that out. The induced EMF now is positive, so if you think about the direction of the A vector, it's pointing out. So if that means that the direction of the circulation will be in the positive sense. The positive sense is defined by putting our thumb in the direction of the A vector. Our fingers will curl. I think you'll see that in this case our fingers curl in the counterclockwise sense around the loop, indicating that the induced current will be in the counterclockwise direction. Okay, for this problem there's a key concept you have to understand, which has to do with turns of a wire. Now, if we have one turn of a wire, that just basically means a simple loop. So if the area of that is A0, if we had two turns, it would basically mean two wires, one wire turned into the same shape but turned onto itself twice with the same final dimensions of this, so that the total area within here would actually count as twice the original area. And if you have multiple turns in here, the total area that comes into the flux calculation is really n times the area of any one loop. And that's because the magnetic field passes through all of those loops, and each one contributes its own flux to the net flux through the loop. Okay? So to apply that to this situation, we'll write down Faraday's law. It's minus d phi dt, but we'll note here, since we've got n loops, the flux will be n times the area of one of the loops, or one of the turns, times the magnetic field. So you see here in this problem, you also notice that there's the n, number of loops, or number of turns. There's the area of any one turn. And this is the magnetic field, which varies in time. Okay? All right. So now that we have that down, let's continue on evaluating this. The n and the a naught are constants. So we just have the time derivative of the magnetic field coming through. Now let's expand this a little bit. The area of any one turn is a squared, and the magnetic field is given by this expression. So now you see all we have to do is take the derivative of this. Now the derivative of 1, of course, is 0, And the derivative of an exponential, let's write down our prefactors here. Oh, I forgot to mention, of course, b naught comes out front because it's a constant, right? So now we have the derivative of this exponential. Well, the minus sign stays there. The derivative of an exponential is the same exponential times the derivative of what is in the exponent, which is just minus k. So the final answer here, because there are three negatives, we have a negative sign, n a squared b naught k e to the minus kt. Now you'll notice that this is a negative number, and we were really only asked for the magnitude of the EMF. So we can write, the magnitude this way as a positive number. And that is the final answer.